Hi, welcome back to this next part of our information about analog to digital conversions with reference to what's happening in the AVR microcontrollers. So I want to have a look at this voltage resolution again, just to make sure that you've thoroughly got a good understanding of it. Say, for instance, it's the difference in voltage required to take the ADC from one value to the next. So here's a couple of values. Here's 75. And here's 76. And of course, it depends upon the voltage reference you're using. So in this first example, I'm going to use 1.1 volts, which is the internal voltage reference of the microcontroller. And in the second example, I'm going to use 5 volts as the voltage reference. And so, for instance, if we're trying to convert a voltage which will give us the ADC value 75, then that works out to be like this, 0.08 volts, okay? Now, if we're doing that, the next step up is 76, so this is 0.0817 volts. So you can see there's a difference between these two of 0.001075, so about 1.1 millivolts, which of course is just this ADC reference voltage divided by the range, 1023 in our case. Now take, for instance, the 5 volt as our reference. And you can see that a 75 comes from a voltage of 0.366569 volts, and a 76 comes from a voltage of 0.371457 volts. And so the difference here is 4.8 millivolts. So really we're looking at the difference between, close to 1 millivolt and close to 5 millivolts. So this is the ability for our system to recognize a change in voltage coming in. So this one has a higher resolution. Perhaps it's more sensitive to changes in voltage. Now, of course, if we're thinking about this, which is better? And this is what it comes down to in engineering. Just because one looks better doesn't necessarily mean that it is better. And so actually the smaller step size allows us to resolve smaller changes in input voltage, allowing us a truer representation of the input. However, better relates to context. And in engineering, a system needs to be fit for purpose. It's quite conceivable that neither of these would be fit for purpose for some systems. And it would be quite conceivable that both of them are fit for purpose for some other systems. So this is what it really comes down to, is making this decision based upon the situation that you're working in and what you're looking at. If you need something more complex than that, then there are more complex analog to digital converters around. For instance, even the ESP32 that was used in 101 and promoted there as a sort of intro to generally to microcontrollers, it had a 12-bit ADC. And you can buy ADCs which are 16-bit. And yeah. So there's all sorts of things available. It's just a matter, again, of just understanding what it is you're thinking about using it for and understanding the limitations of what you can do with your system. That's engineering coming down here. Let's have a look at the actual chip that we've got. So we've got this 80 mega 328P, and this is a particular package of the chip. If we look at the data sheet, let's just pop this open. There we go, and we look at the overview, and we'll find where's the packages, actually the pin configurations. There we go. So this is the package we're looking at here. This is what's actually on our nano board, this TQFP type package. Or some of the boards, if they've got a slightly smaller one, might be the MLF type one. Okay, but these have the same pinouts. And there's a subtle difference with, for instance, this DIP mean dual inline package. So it's dual inline package. And this, I'm not sure what TQFP stands for, you can look them up if you want to. But there's a number of subtle differences between these two here, but these are the ones we're using. And so I'll just go back and bring those to your attention. So for instance, PC0, PC1, so that's port C, and up to PC5, these are all analog to digital pins, which of course can be used as both general purpose digital I/O pins as well as analog inputs. But on this package, which we don't have on the DIP package, is 86.6 and 86.7. So these are two other inputs to our microcontroller. Of course, on bigger microcontrollers, 80 mega, 64, 128, 2560, all those sorts of things, there's plenty of those in the 8 mile range, that they will have at least these 8, if not more, pins on them as well. So just to be clear that these 6 can be used as general purpose pins, and these 2 cannot be used as general purpose IO pins. They're just generally, they're only available as ADC inputs. So just going down here, let's clarify what that means. The ADCs have 8 ADC pins. Now, just think about that, they only have one analog to digital converter. So when we're looking at the schematic here, you can see here's the ADC, and here's the multiplexer, which allows us to choose which of these input pins and some other options we're going to feed into the analog to digital converter. And that is controlled by this AD mux register here, and these 4 lines, mux 3 down to mux 0, okay? It's fully capable of 16 selections, of course. We don't have 16 possible connections to this mux. Remember, this is an analog mux, not a digital one, so it passes through an analog voltage in the range of 0 to VCC allow through here. But what we do have is we have a couple of other inputs. We can measure the 1.1 volt internal reference, they're called the band gap reference, and then we can measure ground, which is really interesting. You could think that the ground input might be slightly different in voltage to what our other system might be that we're connected to. And then we've got an internal temperature sensor that we can measure. So, and of course, once we've done the conversion, the 10-bit output is fed into these 2 registers, ADC high, ADC low, and together they make up ADCW, which is the wide or register, ADCW or word register. So let's just have a look at this. Here's this register. It's got the selections in here for our reference. We will cover ADLAR shortly, and it's got these 4 bits here and the for choosing which of the inputs. Now, just a correction to the notes, just delete that bit. So we want to write the command to select channel 5 for an analog to digital conversion. Okay, so we want to choose. So we could write this command here. However, there's a problem with this. Okay. And that's really coming back to our understandings about what it means about state in an embedded system and inside a microcontroller. Because the ADC channel is something that you don't just set once, it's something you'll go back to at different times. And you'll think about changing the different channel that you're measuring. So imagine, for instance, that we had already been reading ADC3. And so our mux register looked like this. So we've got our reference set up here. And this bit's unused, and this is ADLAR, which we're going to talk about later. And these are our 4 mux bits, okay? Mux 0, mux 1, mux 2, mux 3. And we've set up to read channel 3, so that's setting up this input here. We're going to read this input here, okay? Now, if we then carry out this command, which we think should set it to 5, well, it doesn't actually, because what we're doing is we're setting these 2 bits here, but we're not clearing this bit here. So what we end up with is the value 7 inside our register, and we're reading ADC input 7 instead of ADC input 5. So again, just coming, this is this whole concept of state. What has happened previously in our system has a bearing upon what is taking place now. Okay, you cannot escape that. So you must think, what I've got to do is actually, I've got to 0 all these bits here. Okay, a couple of ways you could do that. You could, of course, 0 each one individually, but you could just write a line like this, which will allow you to 0 those bits there. And it really, you need to make sure that you understand a line of code like this, what's happening here. Okay, it's really important that what you're doing is you are ANDing some bits with 1 and some bits with 0, and the bits that are ANDed with 0 will be forced to clear to 0, and the bits that are ANDed with 1 will stay as they are. Okay, so the output of this command would be to put all 0s here, and then you can set the required bits with this, and the output of this would be to set just these 2 bits here, which is what you're looking for. Again, let's just give a little example. Say we want to have a measure of the temperature sensor here. So let's just have a think about the temperature sensor. Maybe we should have a look at the data sheet to make sure that we know what we're talking about. Let's go down to the ADC, and temperature measurement is here. It's ADC 8. That's interesting. It's coupled to single-ended ADC 8. Selecting ADC 8 channel of mux reads to 100 enables temperature sensor. Now, if you have a look at my notes, you'll see that this temperature sensor here, it looks like it is on channel A, because this is 0, 1, 2, 5, 6, 7. You would think this is 8, 9, and A. And down here in my notes, I've actually put A, but that is wrong, okay? So you don't make an assumption. Always look in the data sheet, okay? Double check the data sheet, okay? Double check it, okay? Double check the data sheet, right? Now let's have a look at one other little interesting thing here. These, I've already mentioned that this successive approximation process is really a bit complex. It involves counters, op-amp comparisons, actually counting. I should just slip in there for my notes in the future. It's a fairly complex little process. So what we have to do in this case is realize that it takes a while for this to be carried out. So our data sheet again will help us. Let's have a look in here. Starting conversion, pre-scaling, and conversion timing. Okay, so this here is going to tell us by default the successive requires an input clock frequency of 50 to 200 kilohertz to get maximum resolution. If a lower resolution than 10, we can look at this. And then it talks about, and here it is, a normal conversion takes 13 ADC clock cycles. The first conversion after the ADC is switched on takes 25 clock cycles. So that's interesting. Your first conversion can often be wrong after you've turned it on. Okay, just that's part of the understanding of reading this data sheet. But generally it takes 13 clock cycles for it to do a comparison. So that's 13 clock cycles at this lower frequency of 50 to 200 kilohertz. Okay, so that's really important just to grasp that from the data sheet. So say for instance, we've got this prescaler, so we can set up the frequency going into the analog to digital converter. And say for instance, we've got a 10 megahertz crystal, which is not uncommon. We can stick a 2 megahertz, we can stick a 20 megahertz crystal on this. I know in the boards we're using it's 16 megahertz, but in this example I'm using 10 megahertz, okay? And if I've got to divide by 2, then I get a 5 megahertz, which of course is way outside this range. And I've filled in the rest of this table for you. Basically, if we've got divide by 4, we get 2.5 megs, divide by 8, we get 1.25 megs, still outside this range, we can't use this. Going down here, finally we get to 64 as a divisor. That means we're at 156 kilohertz, so that's within this range. And then we can get down to 128, which is 78 kilohertz. Well, it's actually within this range as well, so that's fine. We could use both. This one you might prefer, perhaps because it's going to do a faster comparison, but really it makes a little difference. Okay, so then we've got to figure out how to set this up. Again, this is something you set up once at the beginning of the program, so you only need to set the bits rather than clear any bits. So if I'm going to set prescaler 64, I have to set bits ADPS2 and ADPS1. So that's what I've done here in this register ADC control status register A. I've set ADPS2 and ADPS1. And of course, if I want to divide by 128, ADPS2, ADPS1, and I've got to set ADPS0 as well. So yeah, you should be really familiar and comfortable now with looking at these tables, thinking about which bits you're going to set and for what reason. Yeah, really, you should be right onto this by now. Okay, I'm going to go and stop now, and then I'll come back in the next video to the next section. Cheers.